Hi everyone, my name is Brenda Namumba, a postdoc fellow at Trent University. In this presentation, I will highlight the discovery of widespread tidal debris in the nearby NGC 7232 galaxy group. A brief introduction. One of the key questions to be addressed with SKA pathfinders such as Meerkat is to fully understand the evolutionary history of galaxies. Galaxy evolution, as we know, is highly dependent on environments in which galaxies reside. Galaxies in different environments tend to interact with each other, and when that happens, their properties such as morphology or gas content changes, and that brings about galaxy evolution. We can study galaxy interaction by looking for interaction effects that are seen in form of example, tidal tails, galaxy mergers, and gas stripping. Galaxy interaction can be studied at different wavelengths. However, neutral hydrogen is ideal because it tends to be much more extended than the optical disks of galaxies. It is in these outer skirts of galaxies that interaction effects become more visible. To highlight this, I have shown an example of the famous M81 galaxy group. The figure on my left is an optical image, and the figure on my right is the radio image of the galaxy group. It is clear that we get more information using radio observation as compared to optical observations when it comes to understanding galaxy interactions. Looking at NGC 7232 galaxy group, there are many reasons why we decided to study this group, and I will highlight a few. The figure on my left shows all the detected galaxies in the NGC 7232 galaxy group. What is interesting about this group is that it consists of varying gas-rich environments. Within one group, we have varying gas-rich environments. We have the large IC 5201 spiral galaxy, and we have the famous galaxy triplet that I have shown on the top panel. For this study, the focus is not the entire galaxy group, but I'm focusing my studies on the NGC 7232 galaxy triplet. The second reason why we decided to study this group is that it was recently observed with ASCAP, that is the Australian SKA pathfinder. From these observations, they were able to hint the possible presence of an H1 bridge that should connect the galaxy triplet with its surrounding environment. However, with the column density sensitivity of 10 to the power 20, they were not able to detect this H1 bridge. So we thought, well, using the 4K Meerkat mode, we are going to have the sensitivity of 10 times more than ASCAP, and that would allow us to detect the H1 bridge if present at low column density. The Meerkat observations also have high resolution as compared to ASCAP, and that will allow us to resolve H1 features if present. Last but not the least, this group has been studied using ASCAP, has been studied with ASCAP, ATCA, and so there are some of the known galaxies in this group that can be used for testing Meerkat observing mode, and also testing data reduction routines that are being developed to observe, to actually calibrate and reduce Meerkat's observations. We observed the galaxy group for 15 hours using a single pointing, and we were able to go down to a 4 sigma limit of 10 to the power 19. Data reduction was done using Caracal, and the figure I'm showing on my left is the moment zero map. That's the intensity map of all the Meerkat detected galaxies. As I said earlier on, the focus of this study is the galaxy triplets that can clearly be seen at the center of the moment zero map. Looking at the H1 distribution, the figure I'm showing on my left is the channel map of the galaxy triplet with its surrounding environment. Looking at the different colors, blue represents the known galaxies previously detected with HIPAS, ATCA, and ASCAP. The red represents the newly ASCAP detections, And everything that is not labeled, or the black emission you are seeing that is not labeled, represent meerkat face detections. There are many features that you can see in different channels, such as the H1 tail that become prominent in the third panel. You can see clearly the H1 tail detected with the meerkat. Still on the H1 distribution, the figure on my left is the column density map of the galaxy triplet and its surrounding environment. The three galaxies are labeled. On the left panel, bottom panel, I show the ASCAP detections, and on the top panel represents the newly detected H1 debris. Comparing the meerkat column density map and the ASCAP column density map on my right, it is clear that meerkat detects far much more H1 around the galaxy triplet as compared to ASCAP. Looking at some of the properties of this newly detected H1 debris, it extends over 140 kiloparsec in projection and has an H1 mass more than 50% the total H1 mass of the galaxy triplet. One interesting thing to note also from the H1 column density map is the new H1 cloud near the IC5181 lenticular galaxy. The other thing that we actually calculated from this observation is the H1 deficiencies. The H1 deficiency is generally the difference between the expected mass of a galaxy or a system if it were to be found in an isolated environment and the observed H1 mass. So we calculate the H1 deficiencies of the three triplets and also the H1 deficiency of the entire system. From these studies, we find that NGC 7232 and NGC 7233 are H1 deficient, while NGC 7232b appears to have an excess of H1. When we calculate the H1 deficiency of the entire system, we find that the entire system is not H1 deficient. What does that mean? It means that even if the system is interacting, it is not losing any of its H1 mass to the outside environment as at yet. Looking at the H1 kinematics, with the velocity resolution of 44 kilometers per second, we could not carry out detailed kinematic analysis from these observations. However, looking at the velocity field map on my left, it is clear that the velocities of NGC 7232b are different from the velocities of NGC 7233 and NGC 7232. The velocity difference is up to 200 kilometers per second. And it is also clear that the velocities of NGC 7233 and that of NGC 7232 are similar to the velocities of the newly detected H1 debris. This can be clearly seen when we look at the global profile on my right. The global profile shows the flux density as a function of velocity. The peak on my right shows NGC 7232b, and the peak on my left shows NGC 7233, NGC 7222, and most of the H1 debris is actually associated with these velocities. The question is, since NGC 7233 and NGC 7232 are H1 deficient, is it that they are losing the H1 to the surrounding environment, which is this newly detected H1 debris that we are seeing? For us to fully answer that question correctly, we need high resolution H1 observations, high velocity resolutions H1 observation to carry out the kinematics. And we also need simulations combined with observations for us to answer that question correctly. In summary, we have used the 4K meerkat mode to obtain deep H1 observations of the NGC 7232 galaxy group. The meerkat discovered widespread H1 emission, which extends over 140 kiloparsec in projection. The H1 debris has an H1 mass of more than 50%, the total H1 mass of the galaxy triplets. We find that NGC 7233 and NGC 7232 are H1 deficient, while NGC 7232b appears to have an excess of H1. We also find that the entire system, that is the galaxy triplets with its surrounding environment, are not H1 deficient. The velocity resolution could not allow us to carry detailed kinematic analysis, but that is something we want to actually do in the near future. Thank you very much.